Hi. Um, there are two cables. They have the same length, but they are made of different materials. We've got a Young modulus and a cross-sectional area and a breaking stress for each cable. There's one missing. Calculate the missing cross-sectional area so that both cables extend by the same amount. Whatever load is added. That extension there is a hint at the fact that the stiffness must be the same. Now, how is stiffness related to the information given? Well, if we write Young modulus as FL over AX and then rearrange, we get an equation for F in terms of X. It's EA over L. And it's therefore possible to say that this is a bit like the spring constant of the cable. The lengths are the same, so all we need is the product of EA in each case to be the same. So I need to multiply 102 by 22.5 and then divide it by the 153. And that gives me 15 for the cross-sectional area of cable 2. Calculate the maximum total load they can carry. Well, assuming they share the load equally. So essentially what we're doing here is working out the breaking force, which is the breaking stress times the area. And we can do that for both of these, making sure, I suppose, that I've got the correct units. Millimeters squared are, that's 10 to the minus 6 meters squared, just making sure. And as it happens, that cancels with the megapascals. So for cable 1, it will carry 4,185 newtons. For cable 2, I'll do 15 times 127, and that gives me 1,905 newtons. Which cable will break first? This one. And therefore, with both of those cables carrying that same amount of load, 1,905, I need to double it to get the maximum total load, which is 3,810 newtons.